Statistics and probability go hand in hand because statistics is all about data and analyzing data. Probability is going to allow us to determine how reliable our statistical results actually are. So we really like to study them together. And in this video, we're going to start transitioning to probability, and we're going to start with the simplest kind of probability. So probability is basically just the likelihood of whether or not something will occur. So if I'm trying to figure out the probability that I get heads when I flip a coin, I'm really asking how likely is it that I'll get heads when I flip a coin. Now, the probability of any event occurring, we can always express as either a fraction, a decimal, or a percent. But the value that we get will always be somewhere between 0 and 1, including 0 and 1. So in interval notation, we would express it this way. We would say probability is always going to exist on the interval 0 to 1, and these closed brackets here mean that the endpoints 0 and 1 are included. So here's what we mean by that. If we sketch out a number line, so let's say we have on our number line here 0 and 1, right in the middle is going to be 0.5. If we're thinking about our number line in terms of decimals, we could also call this 1/2, and we could call it 50%. If we're thinking about our number line in terms of percent, we would have 0% over here, we would have 100% over here. In fraction form, this would still just be 1, and this would be 0. So basically, we're just showing this number line in different ways, here in decimal form, here in fraction form, and here in percentage form. So when we say the probability of any one event can take on the value 0 all the way up to 1 and all the values in between, let's think about what we mean. If we have a probability of 1 or 100%, that means our event is guaranteed to happen. There's a 100% chance that the event will happen. So if I asked you, what is the probability that I get either heads or tails when I flip a coin? Well, the probability of that would be 1, because there's no other value I can get if I flip a coin. It's either going to land on heads or it's going to land on tails. It's guaranteed to land on one of those two options. So the probability that we get heads or tails would be 1 or 100%. That event is guaranteed. If I say the probability of an event is 0, that means it's impossible or it's guaranteed not to happen. Maybe something like if I roll a 6-sided dice and the faces are 1, 2, 3, 4, 5, and 6, what's the probability that I roll a 9? Well, none of the sides of the dice are 9, so it would be impossible to roll a 9, so the probability of that happening would be 0. If you see a probability of 0.5 or 1/2 or 50%, that means that an event is just as likely to happen as it is not likely to happen. So we could maybe say something like, same chance to happen or not happen. That would be something like flipping a coin. I have an equal chance of getting heads or tails. So if I asked you, what's the chance that I get heads when I flip a coin one time? It would be a 50% chance because I'm equally likely to get heads or not heads. I have an equal chance that heads happens versus doesn't happen, and we'll look more at that example in a little bit. So then any probability between 0 and 0.5, these could be values like 0.4 or maybe 1/5 or something like 25%. All of these values are somewhere between 0 and 0.5 or 1/2 or 50%, means I have a less than 50% chance that the event happens, which means it's more likely that the event doesn't happen than it is that it does happen. But if I have a probability value between 0.5 and 1, so these could be values like, let's say, 0.6 in decimal form, or maybe something like 7/8 in fraction form, or maybe something like 75% in percentage form, any value that's larger than 0.5 or 1/2 or 50% and less than 100%, means it's more likely that the event does happen than that it doesn't. So we could say a greater chance that the event does happen versus a greater chance that the event doesn't happen. So hopefully that gives you an overview of all of the possible probabilities, from the probability of 0, where something is impossible, all the way up to the probability of 1, where something is guaranteed, and then everything in between. Let's go back for a second to our coin flipping example and build a formula for simple probability. So we said before we were interested in the probability of getting heads when we flip a coin. When we express probability, it looks something like this. So we do a capital P, and then in parentheses here, we put whatever event it is that we're interested in. So we could maybe express the probability of getting heads as P of H, the probability of getting heads. But if we wanted to just generalize this as a formula, we would say the probability of just some event. And the formula that we use, and this is somewhat intuitive, is just the outcomes that meet our criteria divided by all possible outcomes. So let's unpack this formula a little bit when it comes to finding the probability that we get heads when we flip a coin. So a lot of times it's easier to start with the denominator, all possible outcomes. So what are all of the possible outcomes that can result when we flip a coin? Well, if we flip the coin, it lands on the ground, we can get heads. It could land head side up, or we could flip it, it could land on the ground, and we could get tails. The tail side would be up. Those are the only two possibilities. We're going to assume that the coin can't land on its edge, that it's only going to land on one of the faces. So there's only two possible outcomes. It either lands on heads or it lands on tails. There's no other possibility. So all the possible outcomes when we flip a coin will be heads or tails. That's two possible outcomes, which means we could go ahead and put a 2 in our denominator. Now, outcomes that meet our criteria. Well, we want the coin to land on heads. We want coins to be head side up. So the outcomes that meet the criteria that we've specified would just be the one outcome, because you can think of tails as a failure. That's something we don't want. Heads would be a success. That's something we do want. So there's only one outcome that meets the criteria that we're interested in. It's when the coin lands head side up. So since there's only one outcome that meets our criteria, we put a 1 in the numerator. And now we've just calculated the probability that we get heads when we flip a coin. There was one outcome that met our criteria over two possible outcomes, so the probability of this happening is 1/2, or you could think about that as 0.5 or as 50%. If we go back to our chart here, and remember we talked about this when we built the chart, that means that there's the same chance of us getting heads as not getting heads, because we're right at the 50% mark. Now, what about a different example? Let's take a deck of cards, for instance. So a deck of playing cards. Remember that there are 52 cards in a deck. So maybe we want to say, what is the probability that we pull a 7 when we pull one card from a deck of playing cards? Well, let's think about it. So again, let's start with our denominator first, because I think that's easier. How many possible outcomes do we have? Well, if we have a deck of 52 playing cards and we just put them all on the table and we pull one, there are 52 different choices that we have. We could pull any of the 52 cards off the table, which means there are 52 possible outcomes. So we could put 52 in our denominator. And then how many outcomes do we have that meet our criteria? Well, remember that there are 4 of each rank in a deck of playing cards. So there are 4 2s, 4 3s, 4 4s, 4 5s, 4 6s, 4 7s, 4 8s, all the way up to 4 jacks, 4 queens, 4 kings, 4 aces. So there's 4 of every number, 4 of every rank, which means that there are 4 7s. We're only interested in pulling a 7, and there are 4 cards that are 7s in the deck. So there are 4 outcomes we could have that would meet our criteria. So we would go ahead and call this 4 over 52. Now, whenever we calculate a probability in fraction form, We always want to make sure we reduce that fraction to its lowest terms. 4 over 52 is the same as 1 over 13. So we would say the probability of pulling a 7 is 1 over 13. If we want to convert this fraction to a decimal or a percent, we could take 1 divided by 13, and if we round to the nearest hundredth, we get about 0.08 or 8%, which means there's about an 8% chance that we pull a 7 when we draw one card randomly from a deck of cards. So 8%, 0.08, 1 over 13, that's going to be down somewhere around here on our chart, which tells us that it's more likely that this event doesn't happen than that it does, which makes sense because 8% is a pretty small chance. We have a pretty small chance of pulling a 7 versus any other card in the deck. Now, one thing we want to say about our probability formula before we go on is that this denominator of all possible outcomes really should say all possible equally likely outcomes. When we're calculating simple probability like this and we're using this formula, we are relying on the fact that all possible outcomes means all possible equally likely outcomes. So for example, when we flipped the coin, we're assuming that it's a fair coin and that we have an equally likely chance of getting heads as getting tails. When we drew a card from the deck, we were assuming that it was a fair deck with all 52 cards that were supposed to be there, and we have an equally likely chance of pulling any one card out of the deck. If our outcomes are not equally likely, for example, if the coin is a weighted coin where it's weighted to land on one side more often than the other, or something about our deck isn't fair, or we're rolling a dice and the dice is weighted to land on one or more sides more often than certain other sides, any kind of scenario where our outcomes aren't equally likely, then we can't use this simple probability formula. We have to use a different formula. This one is just when all possible outcomes are equally likely. So that's the one thing we want to say. And then the second thing we want to say is we just want to define all possible outcomes as the sample space of our probability. So we call this the sample space by definition, and it just means all of the outcomes that could possibly occur. So the sample space of flipping a coin is getting either heads or tails. The sample space of pulling one card from a deck of cards is all 52 options that are in that fair deck. Now let's talk through a bit of a tricky question when it comes to simple probability. Let's say that I have a fair coin, and let's pretend that I flip that coin 3 times in a row, and each time I get heads. So I flipped the coin once, I got heads. I flipped the coin again, I got heads. I flipped the coin a 3rd time, I got heads again. So I got heads all 3 times. And now I want to ask, what's the probability of getting heads? Well, we might look at that example and think the probability of us getting heads was 3 out of 3 because we flipped the coin 3 times and we got heads 3 times. So the probability is 3 out of 3 or 1 or 100%. So we would maybe say the probability of getting heads is 100%. But of course, intuitively, we know that that's not true. We have an equally likely chance of getting heads versus getting tails on any one flip. But this calculation would seem to imply that we're guaranteed to get heads every time we flip the coin. But that's not true. So what's going on here? Well, what's happening is we're creating here what's called an experimental probability. So flipping a coin 1 time is called an experiment. Drawing a card from a deck of cards 1 time is called an experiment. Rolling a dice 1 time is an experiment. So each time you perform an action, that is one experiment. And when we flip a coin 3 times in a row, we're performing 3 experiments on that coin. If we perform the same experiment over and over and over and over and over again, what we'll develop is an experimental probability. And of course, that experimental probability can change depending on our results. So let's say I flipped the coin 3 times and I got heads each time. I would say the probability of getting heads is 100%. But let's say instead that I had flipped the coin maybe 5 times, so probability of getting heads, I flipped the coin 5 times and I got heads 4 times. I might calculate that the probability of getting heads is 4 over 5, which would be 0.8 or 80%. So I'm getting a different probability of getting heads each time I run an experiment. This is different than what's called the theoretical probability. The theoretical probability is what we tend to think of when we think about probability, because it's the likelihood that something will occur if you run really an infinite number of experiments. You almost want to think about it as true probability or real or actual probability, because we all know that the probability of getting heads when I flip a fair coin is 50%. That means my theoretical probability of getting heads is going to be 50%. But I can run a bunch of experiments, and depending on how many experiments I run and what my results are of each experiment, I can get a different experimental probability. What we know is that the more experiments we run, the closer the experimental probability will get to the theoretical probability. And this is often what we call the law of large numbers. It tells us that the more experiments we run, the closer our experimental probability will get to our theoretical probability. In this course, we're going to be focusing mainly on theoretical probability because that's the probability that we're really interested in. We don't really care so much right now that if we run a different number of experiments, we're going to get different results for the probability of an event happening. We want to know the theoretical probability of that event. We want to know that the probability of getting heads when we flip a coin is 50%. We're interested in that expected probability, that theoretical probability. So that's the one that we're going to be focusing on.